Hi, today I am assigned the topic tight binding model. Here in the tight binding model, what we study is the interaction of tightly bound electrons of atoms of one atom with tightly bound electrons of another atom. So for that, what we do, we write the wave function of the atomic orbital of any atom like as it would have been in isolated state, and then we generalize that for the one-dimensional crystal lattice. As the atoms are discretely located in the one-dimensional crystal lattice, as I am having the diagram here, we assign in order to generalize that the atomic orbital wave function, we write phi v x minus xj. Now it's generalized. The xj can have any value in multiples, integer multiples of a. A is the period of, or the gapping between any two atoms, nearest neighbor atoms. And then there is another term, the periodicity. We multiply with that, and then we get a superposition of orbital wave functions of all the atoms in the one-dimensional crystal lattice from 1 to j. And then we write it in blocks style. We multiply with exponential minus ikx and exponential plus ikx. This can be like this, written like this, and can also be checked. If you put xj equals 0, then the wave function would come for the atom which is at xj equals 0, and this is the phi vx. And as we know from quantum mechanics that the total energy can be written like this: the Hamiltonian, sandwiched, the states bra and cat. Now we write the total energy when the atoms are interacting. The generalized term, when the atom at jth location is interacting, at jth location anywhere here, interacting with at j-th location anywhere in the crystal. And this is the expression for, and we write in convenient style. And now in order to study the interaction, we put xj dash equals to 0. That means we take one particular atom which is at xj equals 0 and consider or calculate its interactions with other atoms in the crystal. So for that, we write this. If you solve this somewhat, we get this expression. This is the energy the electron would have had in the orbital phi nu x when the atom would have been in isolated state. But here the atom is not isolated because atom is in the crystal and there will be interactions with other atoms. As we write the Hamiltonian crystal kinetic energy part plus potential energy part. This potential energy is the total potential energy at x, where this x is corresponding to the coordinate axis where we would take along the crystal. So this can be broken into two parts. The first one is the potential energy of the atom itself, and another is because of interaction. And like that, these can be plotted for the atom at j equals 0 and for j equals to minus a plus a. And now this is in this expression we try to calculate the energy of the electron when the atom is in the crystal. The first is EV, the energy of the electron would have had when it would have been in isolated state. So atom would have been in isolated state. And another part is because of the atom to be in the lattice. So we replace the second part with minus beta, and we get minus beta equals to this much. and this part is this, because the style of writing is different. Here it's written in bracket notation, and here I've written it in the wave function notation. And then we put this beta and EV part here in the same equation, equation 4. We get this, the equation to be this much. Let me get. Now what we do, as we have calculated the change in energy or the total energy of the electron when the atom is in the lattice. Now another thing is that, as this is tight binding model, we will study the interaction of the atom of the adjacent atoms. Here I take the atom which is at x equals to 0, the uppercase x equals 0, and another atom which is at x 1 equals to a. So we try to calculate this interaction term. So as this is tight binding model, I've already explained that there would be less overlapping. So this term is approximately 0. Only this term is left for the interaction. And we replace this with minus gamma and write that in wave function form from bracket notation to integral notation here. And then we get we come here. This is the total energy of the electron now, because of all the interactions. This part is there, and this part of interaction. And as the electron can interact with the, means the atom can interact with the adjacent atoms. That's why we can put xj equals to plus minus a. And if we solve this, we get this type of expression. And on being solved a little further, we'll get this expression, where E naught equals to E nu minus beta minus 2 gamma. This is a constant part, and the rest is the variable part, which is depending on on k. So now what has happened here, the Ek is having the minimum value E naught. So the bottom of the band is having energy E naught, and the top would be when k times a over 2 equals to pi by 2. That would be Ek equals to E naught plus 4 times gamma. So there has come a band of energy. This is the gamma is the width of that energy band. And now we come here. If the k value is smaller or close to 0, then this expression becomes this much, and this is the potential energy part. So total energy minus potential energy, this is the kinetic energy part. If you put that equals to the kinetic energy formula, h cross square k square over 2m star, we get m star equals to h cross square over 2 a square gamma. This is the effective mass here. And this is because when the atomic orbitals of adjacent electrons overlap with higher value of gamma, then the effective mass is small. Why is it so? Because if the overlapping is larger, then the electron can move easily, and the terms we can say that there is less inertia, and inertia property is itself mass of electron. So if there is less gamma, then m would be greater, the inertia property is greater, and the effective mass is larger. And similarly, if we calculate that for top of the band, then we write k less equals to pi by a minus k, and we end up with, by putting that equals to kinetic energy equals to, from the kinetic energy formula, we end up with m star, the effective mass, to be negative. So these were the consequences of the tight binding model. Thank you.